Welcome back to Lawrence Tech in windy Southfield, Michigan today. I'm Jim Kearns, and today we're going to do an example where we're going to simplify a set of loads and a couple on a rather arbitrary shape here, just to walk through the process of reducing these to a single force and single moment at a point. We'll do it at point A, and then we'll take the next step to reduce that to a single force at a specified distance that gives the equivalent force and moment effects as the two forces in one couple we have drawn here. So if we look at this in a little more detail, I've got my 80 Newton force out here at a total distance of 13 meters from the left end. I've got another force here of 120 newtons that's at a 30-degree angle pointing towards the upper left. That's 8 meters from this end, and it's also 3 meters down from the center. And I have this couple right here of 150 newton meters that's just applied at an arbitrary point. And for the sake of reaction forces and combining forces into a single force couple pair or even a single force, it doesn't matter where I apply that couple. I could apply it where it's drawn, I could apply it here, I could apply it there. It gives me the same answer because when we're looking at external reactions, we consider the couple to be a free vector which we can apply anywhere. And if that doesn't make sense, then if you want to understand the explanation, I'll put a link somewhere about here that you can click on to a previous video where I go through that and explain why that's a free vector and why you get the same answer no matter what. The first step is to draw a free body diagram. That looks very much like the original drawing. I've just added a reaction force, or a resultant force, excuse me, and a resultant moment at point A that we're going to try and turn these into, and then at some point we'll find a place to apply a force that covers everything with just one force. So we'll start with the easiest parts. I can resolve this 120 Newton force into X and Y components using Cartesian notation. My resultant force in the X direction, R sub X, is going to be equal to the sum of the forces in the X direction, all the externally applied forces, and that's just simply equal to, it'd be negative because it's pointing to the left, negative 120 times the cosine of 30, and that gives us negative 103.9 newtons. And in the Y direction, my resultant in the Y direction is just the sum of all the forces in the Y direction, and that's equal to a minus 80 newtons, that one. The Y component of this force plus 120 sine of 30, and that's all of those, and that is equal to net of minus 20 newtons. I can then combine those X and Y components to give me my vector R. The magnitude of that vector is square root of the X component squared, 103.9 squared, plus the Y component, which is our negative 20. I'm going to ignore the negative sign since we're squaring it. 20 squared, and that gives us a total magnitude of 105.8 newtons. And for our angle, theta, that's going to be equal to the inverse tangent of the Y component, minus 20, over the X component, minus 103.9. And again, we want to be careful what quadrant we put this in, because if I just do minus 20 divided by 103.9, I get a positive number, which would lead me to an angle that puts it in this quadrant. On your calculator or in MATLAB like I did it, they have a command. There's a command in MATLAB, tan 2, and since we're using it in degrees, I'll say D, A tan 2D, where I give it the minus 20 and minus 103.9, and it will put the angle calculate the angle such that the vector points in the correct quadrant. So that gives me an angle of minus 169 degrees if I did everything correctly. So up here I can label my resultant force here as having the magnitude of 105.8 newtons and an angle here of minus 169. Okay. My resultant moment at A, it's going to be equal to the sum. It's going to be equal to the sum of the moments about A plus the sum of any couples that exist, okay? And we do have one couple in this case. That is going to be equal to, summing up my moments, I've got my 80 Newton force, and that's at 13 meters, and that's going to generate a clockwise moment, so that's a negative 80 times 13. I've got the vertical component of the force here from this. That's going to be counterclockwise, so that's positive 120 sine of 30 times the distance 8 meters times 8. And I have the x component of this force, and that's going to, which is at 3 meters down here. So that's going to generate, again, a clockwise moment, so that'll be negative. So negative 120 cosine 30 times 3 meters. And then I have my couple, which is drawn as counterclockwise, so I have minus 50 Newton meters for that couple. And when I put all those together, I come up with a moment of negative 298.2 Newton meters applied at point A. So that takes two forces plus a couple and brings us down to one force and a couple. It might be nice to further simplify this and come up with a single force applied at some distance. As I move this force over this way, obviously I'm generating a moment at point A. So what I want to do is find the point, the distance, where the moment of our resultant force, R times D, is going to be equal to the moment about our resultant moment at A, okay? And then that will give me that resultant moment without applying a separate moment. So what I need to do is rearrange that a little bit, and I get the distance is going to be equal to the moment resultant at A that I had before, divided by, I only need to consider the y component of that resultant force, right? Because the x component of that resultant force doesn't give us any moments at all. So I can just look at, and I'm moving it in the x direction, okay? I should have said that up front. So moving it in the x direction, I only have to consider the y component of my resultant force. That's equal to my minus 298.3 divided by minus 20, and that gives me a distance of 14.9 meters, which is somewhere over here. So I'm going to take this moment in force that I'd calculated previously, and I'm going to replace those with a single force with that magnitude of 105.8 and an angle from our axis here. Well, let me move some things here. This angle here we calculated to be 169 degrees, and the magnitude of this was 105.8, and it's applied at a distance of 14.9 meters. Okay, so it's actually being applied somewhat off the end of that body physically, but if we ignore that little deviation from reality from a mathematics perspective, or from a perspective where we're looking for reaction forces or anything else, we can just assume that the force is applied there, even though it's not physically touching. So that wraps this up. I hope you found that helpful, and we'll catch you on the flip side. Bye.